So we now have looked at if we have four or more terms after we factor out the greatest common factor, we're going to do factor by grouping. And then if we have three terms, if the coefficient of the squared term is 1, we just go ahead and break down the factors of the last term, find the ones that add up to the middle term, and then write our factorization. If the coefficient of the squared term is not 1, then we need to factor it by the AC method or by trial and error. And then we also saw if we had a perfect square trinomial. So we now have talked about a factor polynomials have four or more terms. We have talked about how to factor polynomials with three terms. Now we want to take a look at one that has two. And this is called a difference of squares. And the idea is if I FOIL this, product of the first would be a squared. My outer terms would be ab, but my inner terms would be a plus ab. So if we have a minus ab plus ab, they're going to add to 0. And then b times b gives b squared. So if we have exactly the same two binomials being multiplied together, except for the sign in between the terms is opposite, then the middle terms are going to add to 0, cancel out so to speak, and that would just leave you the first term squared minus the last term squared. And this is now called the difference of squares. And so in this section we're going to go backwards. We're going to give something in this form, we have to break it down this form. Now caution, this only breaks down to difference of squares. If it's the sum of squares, you cannot factor it in the real numbers. You can actually factor in something what they call imaginary and complex numbers, but when we're factoring, we're going to stick to the real numbers. So the note here is that if a and b are shown no common factors other than one, then the sum of squares is not factorable over the set of real numbers. So that's just what we said. So, well, let's take a look at these. So what I want, there's three things I'm checking. Is the first term a perfect squared? Is the last term a perfect squared? And do I have subtraction in the middle? So on this one, the first term is a perfect square. That's going to be x. The last term, I guess I did that wrong. Try that again. So a here would be x. My last term is a perfect square, so b would be 5. And we do have subtraction. So all three things check out. So this is going to factor. Is x plus 5 times x minus 5. Let's try number 2. Let's make 2 a little bit more interesting. I'm going to make this a 9x squared minus 1. Just make it a little bit more interesting. So a here would be 3x. B here would just be 1. And you ask yourself, do I have subtraction in between? Yes, I have subtraction between terms. So we're just going to go and factor this as a difference of squares. So the first term is 3x. Last term would be 1. Let's try problem number 3. We have m squared minus 49. So a here would be m. Square root of 49 is 7, so b would be 7. And we do have subtraction between the terms. Now, just a comment. It really doesn't matter if I put the one with plus in the middle first and then the one with negative in the middle second. I could have just as easily put the minus first and a plus first. It doesn't matter. The reason is that multiplication is commutative. I can switch these orders, so I could state it this way. and this would also be correct. I also have to state that because I'm used to putting the minus first. I always like to get the negative stuffs out of the way before doing the positive stuff. Let's try number 4. And here I'm going to change number 4. I'm going to make this a 4x squared minus 121. So a here would be 2x. B would be 11. We have subtraction between. So we can break this apart. Get 2x and 11 for B. So that gives us 2x plus 11 times 2x minus 11. All right, let's try 5, and I'm going to change 5. I'm going to make it more interesting. I'm going to make it 9a squared minus 81. Now, you look at this, 9a squared is a perfect square trinomial. 81, no, sorry, it's a perfect square term. 81 is a perfect square term. But notice they have a common factor of 9. So actually, I want to factor out that greatest common factor first. And now I'll break down the stuff inside the parentheses using our difference of squares. So here a is going to be equal to a. That's kind of weird, isn't it? B is wrong color. I need to use green if I want to be consistent above. So B here would be 3. And so this would factor into a plus 3 times a minus 3. Now, if I type that in my answer, as my answer in ALEKS, it's going to stick out its tongue at me and saying, you're wrong. Because don't forget, we took out a common factor of 9. All right, let's look at number 6. We have x squared plus 25. And the first term is a perfect square. Last term is a perfect square, but we got a problem here. There is a plus sign. We cannot factor this as prime. It's got to be subtraction. All right, see, look at number 7. It says create your own difference of squares problem. Okay. I guess we can do that. How about 15x? Now let's make it, not 15, my bad. Let's make it 45x cubed minus, let's see, let's do 80x. Now you're probably thinking that I've completely gone off my rocker because like, how's that a difference of squares? Well, at the outset it's not, but notice you have a greatest common factor. Greatest common factor here is a 5x. If we factor it out, that gives us 9x squared. 80 divided by 5 is 16, so that's minus 16. And so now we have a difference of squares. A here would be 3x. B would be 4. Again, I'm just going to bring that 5x across. So that gives us 5x times 3x plus 4 times 3x minus 4. All right, it says create a sum of squares that's prime. All right, well, let's do that. How about if we do 12x squared plus 75y squared. So we can factor out the greatest common factor. The greatest common factor here would be 3. That would give us a 4x squared plus 25y squared. And then that's a sum of squares, so that cannot be factored. Now, just a quick comment on these. And maybe we should go back to, I'll just do a different example. Let's say we went back to number 3, and let's pretend this problem had been, so I'll call this 3b. Let's pretend it had been m squared minus 49n squared. You still do exactly the same thing. You'd still say a here is m. B here would be a 7n. So the way your answer would change then is that you would just have n's here after the 7s on each of those last terms. See if I can squeeze it in here. But it works exactly the same way.